All right, we begin meteorology, going back to make sure we understand the Earth-Sun relationship. So, incoming heat is being absorbed, right? Visible light, shortwave, is being absorbed and re-emitted through the atmosphere from the ground up. This is in the form of long-wave radiation. Here we're really looking at the Earth's heat budget, that it's going to be the sun that's going to be driving heat differentials, and that's going to lead to, let's say, both moisture in the atmosphere and warm air to rise. And when it rises, we're going to start seeing that, well, clouds are simply a consequence of that rising air with moisture. So the atmosphere is heated by the ground up. Make sure we reiterate that. Some materials absorb more energy and other materials reflect more energy, right? And that's a reflection of albedo. Organic materials such as plants and animals tend to absorb more energy than barren deserts. Therefore, the arid temperature in a forest is usually cooler than the temperature in a desert. Likewise, the blacktop roofs of buildings in a city act like a desert, raising the temperature of an area by as much as 10 degrees. Water absorbs vast amounts of energy from the sun. Likewise, bodies of water release more energy, or release energy very slowly. For this reason, areas of water are usually more mild. So we'll look at how and why oceans or large bodies of water influence the land around them. And this is a function of the specific heat, water's ability to absorb and store that heat and release it later. The atmosphere itself is going to be broken down into, really, we can consider this stratified much like that of rocks. Rock strata are just layered sequences. So the troposphere, the stratosphere, notice the pink line here is our ozone, it's labeled right here, the mesosphere, and the ionosphere. That these each have different characteristics. However, it's the troposphere that's our primary, let's just say, point of attention for this unit. This is where all weather takes place. Life exists, and our atmosphere consists of 78% nitrogen, 21% oxygen, a little bit of argon, water, carbon dioxide, and other trace gases. And this ranges from 4 to 12 miles, or 7 to 20 kilometers. So what is weather? Well, these are the immediate conditions of atmosphere. Weather is basically the way the atmosphere is behaving, mainly with respect to its effect on life and human activities. Weather can change from minute to minute, day to day, seasonally, with a wide range of variability. So some weather terms: temperature, humidity, precipitation, cloudiness, brightness, visibility, wind, atmospheric pressure, high or low. The graphic to the left indicates warm weather occurred in the Midwest for a 3-month period. Several locations have temperature anomalies that range from 4 to 6 degrees Fahrenheit above average conditions. A few locations were below average conditions. Climate is how the atmosphere behaves over long periods of time. When the word climate change is used, this references long-term averages of daily weather changes. So the sun's going to warm the equator more than the poles due to the angle of incidence and insolation at equatorial latitudes. Climate follows this general warmer pattern. So regional climates can vary based on elevation, location or proximity to water, latitude, the terrain itself, season, etc. So there's a lot of variables that we're looking at as we measure and still continue talking about weather and climate. I think one good piece to make sense of weather, you can look outside your window and see weather. Climate is something that takes place on a larger scale. So we're going to be studying Earth's oceans. So there'll be a little bit of oceanography in all this. But oceans of the Earth, they transfer heat that's absorbed at the equator, and they transfer it to the poles. This is just essentially the massive ocean currents. These currents are like rivers flowing across the vastness of Earth, bringing warm waters from the equator to the higher latitudes and cooler water from the high latitudes down towards the equator. So it's a circulation that's transferring heat. So we learned that the greenhouse effect is very normal. It's very normal. It's actually a good thing. It actually keeps the temperature component of Earth to a liquid water condition. And we studied this in the form of the Goldilocks effect, and the atmosphere also plays into that. So it's the right distance to allow for the characteristics for liquid water. So as we continue moving forward here, we're going to be studying a topic called latent heat, and this is what we'll be doing labs. We need to make sure that we understand that the Earth's atmosphere has the ability to store heat. Now, it's nowhere near that of the oceans, but when heat is stored, it is referred to as latent heat. As water evaporates off the surface of a lake, this stored heat is carried into the atmosphere. As water condenses, forming raindrops, this heat is returned back to the Earth. It is this very heat energy that drives weather. We can't ignore the water cycle. We're going to be looking at most of the water cycle in its vapor form. In the Earth's distribution of water, you're going to find that fresh water on Earth that we consider is actually, well, when I say fresh water, non-saline or saline, or at least accessible, because notice we have groundwater at 30% in glaciers and ice caps. Most of the Earth's accessible fresh water is actually from ice and snow. And last but never least here, there we go. And last thing I want to make sure we clarify here, it's the sun driving the water cycle. The sun's heat is creating differences of temperature. Warm air is going to rise and cold air is going to sink. And when you couple that with what's happening with water vapor in the atmosphere, you're going to start having clouds, and clouds are going to start leading to precipitation. And we can calculate that, it's mathematical, and we can start understanding it conceptually. There's an introduction.